Hello everyone, welcome back. This is going to be the first lecture for our second semester in our blockchain fundamental course. Now, last semester we have covered a lot and we're going to do a review later on just in a minute. But for this one, we're going to do a deep dive on Ethereum. So last semester, Derek have already covered the basics, what Ethereum is, how it came about, how does it solve the limitation of Bitcoin scripts, the Ethereum virtual machines, as well as gas costs, all those concepts, right? But then later on, what we realize, and by hearing from your feedback, is that you still don't know how it works. Essentially, those are very high-level abstracts, pretty theoretical, but from a developer perspective, probably there's still a few pieces missing, right? You know all those pieces, but you don't know how to put them together when you're developing like this centralized application. So that's what triggers us to do another deep dive into Ethereum. And the goal for this lecture is basically presenting to you my mental representation, my mental model of Ethereum, and gonna give you a nice abstractions at different levels. Okay. And by the way, my name is Alex, and let's just dive into it. So let's do a very quick review of what we have been doing for the last few months, and some of the lectures that we already have. In the first lecture, we cover the cryptography basics and an overview of the Bitcoin protocol. We started out by giving a motivation of Bitcoin. What happens? What are some of the digital currency systems that we already have prior to Bitcoin, and what drives a group of cyberpunks and sometimes anarchists to and cryptographers and distributed system experts to design this Bitcoin systems. We talk about the basics in cryptography, including digital signatures, hash functions, and some of the important data structures that are used heavily in all of the cryptocurrency systems that we've seen today, including like hash pointers, the unspent transaction output models, and the Merkle trees, which we used to store and organize structure our transaction so that we can have a more efficient proof of membership. And also in our first lectures, we introduce what does it mean to have an identity or to have an account on blockchain, because we did a very simple comparison with the current banking system, where each account is basically uniquely identified either through your social security number or some personal information of yours. But then on the blockchain, you can have multiple identities, because your identity is essentially a hex string, which is your public key or the hash of your public keys. So and this key generation for this key pair, right, the private and public key pair, is public. Everyone got the algorithms, and so essentially you can create as many identities as you want. That's where people say that you were basically pseudonymous on Bitcoin. So that's what we cover in the first lectures. Then we move on to the second lecture, where we talk about how do we achieve a distributed system, right? How do we achieve consensus distributedly instead of like having a central authority, like in the traditional banking system, where every transaction goes through a central server who handles all the transaction and who is the ultimate authority to say what's the current state of the current ledger, right? So that's where the second lecture covers Nakamoto consensus and the actual Bitcoin protocols. So we talk about distributed consensus and the proof of work, which is a algorithm that we use to decide or to randomly choose someone from this entire pool of miners and have him to propose the next block. Then combining with the longest chain weighing this rule, we got the Nakamoto consensus. Then after presenting how the Bitcoin protocol works, we have a step-by-step step through of the entire protocol, and we have a brief analysis of how secure this Nakamoto consensus and this proof of work is. What are some of the incentives for the miners to maintain and keep mining, right? We talk about the mining pools, which is a phenomenon that derived naturally from this design. We'll talk about some hard forks and soft forks. Then in the third lectures, Derek give very nice introduction to Ethereum. We started out by describing the limitation of the Bitcoin design and some of the, especially the Bitcoin script, which is quite limited in terms of expressiveness. And we talk about how Ethereum want to be a more general purposes, world computer by, designing a virtual machine that is sort of Turing complete. And we talk about how account and transactions are being presented in Ethereum, what are some of the differences between the two cryptocurrency systems, and we introduced a very interesting idea that Ethereum introduced to us, which is gas. What do you mean by gas? And just to refresh your memory, it was initially proposed because we want to avoid denial of services attack, where people send a transaction or send a state updates that essentially could take forever, or if you can imagine the infinite loops that someone required the entire network to run through, and that is definitely not desirable. So to avoid that, what Vitalik originally designed in the white paper was Ethereum white paper was basically saying, hey, everyone have to pay a certain transaction fees in terms of gas, and when you run out of gas, in the sense that you're asking all the miners to compute so much that you didn't pay enough, then they just drop and revert all the state updates instead of like running your heavy computational task that you just give everyone in the network to do. So that was the third lectures, and then in our fourth lecture, which is the last one last semester, we introduced the popular term smart contract and Solidity, which is one of the most popular programming language that you can use to write smart contract on Ethereum blockchain. We introduced the why, the what, and so what. We have a crash course on the basic syntax of the Solidity programming language. We have some live examples as well. Now, that's what we have been doing for the last semester in our blockchain fundamental course. If you have any questions or doubts, or you forget some of the content, I would strongly encourage you to go back, and because we have recordings for every sessions, and for those of you who are watching online or who are not part of Blockchain NTU, you could join our Telegram group, which I will I'll present the link at the end of this talk, and you can join the Telegram group. We put everything, all of these information online, and wanted to make it accessible to the public as well, and all of these are free. Now, before we move on to what we're going to do for this semester, we hear some of the feedbacks that you give us. The first feedback is that there are just too many theories, and it doesn't seem like I'm learning anything very applicable. And I think this is a very legitimate concern, because at the start, what we set out to do is sort of like, we want to build up your foundation first before we introduce those engineering techniques or like the programming side of things. But then later on realize that it's probably too abstract to talk about such an interdisciplinary fields without giving you something you can actually do and get your hands dirty. And so that's why from this semester onwards, we're gonna put more emphasis on the hands-on practices, and we're gonna do so during our weekly sharing sessions. And these weekly sharing sessions gonna be internal events, internal tutorials kind of. So we'll have later on we'll show you some of the plans that we make and the calendars for this semester. Now, the second feedbacks that we often hear is that I don't have a particularly strong CS background. I'm not from computer science, so I find so many of the concepts very hard to capture or to understand. So in order to help people or members who have these problems, first of all, our education department has prepared a question boards. It's like a pin board where you can upload or submit the questions that you don't understand, and there's no stupid questions there. Everyone is basically learning from each other. So whenever you're posting a question there, people from education department, and me myself included, is gonna try to help you answer, at least point you to some resources that we find very helpful to us when we started learning these stuff. Okay, and the second thing is that we have a Slack channel, and this is internal. So we have 3 dedicated channels for this. First is Quora, the second is Stack Overflow, the third is research. The first Quora is for general questions, regarding to blockchain or computer science in general. Stack Overflow is more of a programming related If you don't know how to debug when you are like, I don't know, on Windows machine, try to npm install Web3, and you usually encounter some, dependency issues, how to resolve it. Those questions can be asked in the Slack Overflow channel. Then the last one is the research. So this is typically for the R&D department, people in R&D, or you look at if you ran into a new paper that you find interesting and you want the R&D people to present or to share what they thought of the paper. That's where you can post those information and ask questions in that channel. The third thing is that internally we have event calendars, and we're going to send out this invitation to everyone, every member of our club, so you can have a great idea, a very transparent. We want to make everything pretty much transparent, so you know what's going on, what events you can attend. Even if you're not, let's say, from the R&D departments, every session of theirs, you can still join and opt in. So that's the second feedback. Third feedback is that there's nowadays there are too many new concepts coming out, new protocols, like every other week. So I really don't know what they are, and I don't even know where to start, which paper should I start reading, and I don't know whether I should care about them. Some of them are have higher quality than others. So in order to solve some of the confusion there, we were going to be hosting a SOK sharing sessions probably in week 6 or 7. Now SOK stands for System of Knowledge. So basically, we're going to cover all of the research frontiers in this space, including the scalability issue, the security of blockchain, privacy-preserving technologies, formal verification, formal methods, P2P network, and consensus, all different consensus algorithms, and the key managements. All of these topics, and what are some of the status quo or state-of-the-art research. And we're going to present it to you, at least to give you an idea whether what people are exploring nowadays, and what are some of the links or resources that you can keep yourself up to date. So that's we're gonna that's the one particular session that we designed particularly to help you be more self-motivated, and so that you can move forwards in your free time. And then the advice that we give, of course, is to read a bunch. Right, and to encourage you to do that, if you read something or if you spend a lot of time researching on one of these topics, like for example scalability issue, if you read a lot on Plasma or on state channels, what you can do is that you can write up your thoughts and what you've learned, and we can try to publish that through our blockchain medium, blockchain NTU medium. So, well, the last thing is that the best thing to feel yourself, at sort of at stakes, is to get a job, and that's where you will learn things, at the first hands. So that was the feedback. Now move on to the preview for this semester. So for this semester, we'll still keep the two original formats. One is the bi-weekly lectures. The other is the weekly sharing session. During the lectures, we started out with the Ethereum deep dives and presenting to you as a developers, right? What's my perspective and how do I look at blockchain? Then we move on to some development framework, Truffle, and how do you write testing scripts, which is essential if you want to develop something that's production ready, or that people actually uses. Then we move on to blockchain sharding, and this lecture is going to be given by Zileka, who in my opinion is one of the pioneers and also the best company who are doing blockchain sharding right. Then we'll move on to smart contract security. What are some of the common vulnerabilities? And we're going to analyze some of the major attacks that have happened on the Ethereum blockchain or some other blockchains as well. Then we'll move on to Web3 library. We're going to give a in-depth introduction to how to use Web3.js or Web3 library to build up your front end for decentralized applications. How do you talk to the blockchain at the back ends? So that was for the lectures. Then for weekly sharing session, as we say, we're gonna be more hands-on oriented. So last week we already covered the basic developer tools given by Derek. Because we recognize that some of you are not like web developers or mobile developers. So we just want to basically introduce those tools to you, some of the popular frameworks that people use to build mobile applications or web applications. Then we'll move on to a lot of lab sessions on smart contracts, and we're going to do so in a more interesting way, instead of just to give you dry content about the syntax and reading through the documentations. Well, the documentation is important, but we're gonna use crypto zombies, which basically gamify by Loom Network. So they basically gamify the process and gives you a very nice tutorials that you can actually follow along. And they broke those syntax into pieces so you can follow along more easily. Then we have a sharing session. Again, I have a sharing from Ethereum Foundation. So one of the guy, I think I forgot her name. I think she's looking for some internship, for some interns, for the Ethereum Foundation, and then she will have a sharing of Ethereum 2.0 specs and current roadmap, etc. Then followed by the SLK session that we mentioned about, for mostly for the current research. Then we're going to talk about, we're going to practice on hacking smart contract. We're also going to do so by playing games designed by the Open Zeppelin team. It's called Ethernaut. We already have like a brief session on this last semester, but this semester we're going to actually finish all of these games during our weekly sharing. Okay, so that's enough for the administrative stuff. Then we're going to move on to today's lectures. Okay. Once again, the motivation for us to do a deep dive is that we believe, although we have already present all those concepts, and what do they all mean? It will essentially it still doesn't help you if you don't know how to put all the pieces together. So like Einstein once says, like, any fool can know. The point is to understand. So the key goal for us today is try to help you understand. Now, there are 3 sub-goals for today. The first is that I want to develop a mental representation of Ethereum blockchain to you guys. Instead of like having a very abstract, scattered around concepts and terms or terminologies, we want to have a more structured, more holistic view of the system. That's the first sub goal. The second sub goal is that we want you to have a micro and a microscopic views. Okay. So lastly, I'll give some concrete examples so that you could have better feeling instead of just listening to me explaining terms. So I think that will probably help on you having a better understanding of all the concepts. So let's start with the satellite level view. So we're going to start with the macroscopic, and then we dive deep and zoom in to the microscopic view. Okay. When we started out as the satellite view, what is a blockchain, right? We ask ourselves as a developers, what does a blockchain, this term, mean to me? Now, there are many answers to that, but to me as a developer, I see it as just a very simple distributed P2P software. Now, that is still a very mouthful term. And we're going to break it down. The first term, which is the more interesting and important one, is distributed. Okay, it's a piece of software, but it's not like any other software. It's a distributed software. What that means, right? There are 3 points to understand. The first is that it is dispersely located rather than on a single machine. Now, imagine you're watching these videos, and I'm using a recorder. I'm using a screen recorder and an audio recorders. These 2 softwares are running locally on my machine, and it is not running on your or other people's machine. So this piece of software is not a distributed software. Okay, so for software to be distributed, there are multiple instances, probably running on geographically located at different places. Now they can be logically at different places as well. Now, we can for now we can just imagine people at different geolocations are running this piece of software. Then we call it distributed. The second point is that since it's not running on a single machine, these two instances or process, sometimes we call, when they try to pass on a certain messages or try to keep each other in sync, you have to pass a message across the network. Okay. So if there is a software or server processes that's running on a single machine, they can talk by writing to the same piece of memory and read and write from that piece of memory or a disk storage, hard disks. But then if they're running on different machines, they couldn't do that, right? Because they do not have a physical access to the same piece of hardware. So what they do when they try to communicate is through passing messages across the network. And that is very important to understand. Now, the last thing, which is basically a side note, is sometimes people refer to each instances of this software as a node, a peer, or a client. Okay, those are just terms that you will usually see. Now, there are two important questions to understand in order to fully comprehend distributed. Now, the first question is, is it true that for all distributed softwares, every node or every peer is running the same piece of code? You can pause a while and think about it. Okay, the answer is not necessarily. Okay, no, not necessarily. And a good example is gonna be Hadoop or MongoDB. If you're from a computer science background, you probably heard of them once in your life, at least, right? So all of these, Hadoop or MongoDB, these are all distributed softwares, but not every node or every peer is running the same piece of code. And for example, Hadoop is using a master-slave model. Let me just give you a brief introduction to this. So in the Hadoop systems, you can think of it as like a system that handles a lot of tasks, all right? That has a good, concurrency and parallelism model. So there are two kind of roles in this Hadoop system. One is called master, the other is called slaves, right? Just judging by their names, you probably already know what they do. So the master are those who are hearing from, it's like a load balancer where you hear from the tasks from the clients who are sending all the tasks. Now, after you're hearing those tasks, master are not the ones who are actually computing or doing those tasks, right? So master is redistributing those tasks into different slaves, okay? So those slaves are the ones who are actually computing or doing the tasks. So let's imagine a client, right, is trying to ask the Hadoop system to compute what is the sum from 1 to 100, right? So the master, after hearing this request, break down this break down this task into different subtasks, and then the slave 1 is in charge of calculating the summation from 1 to 10, slave 2 calculating from 11 to 20, so on and so forth, right? And at the end of the process, every slave is going to report back to the result, and master is going to sort of like add them up and then return the value to the client. Right, so as you can see, so that was probably not a very good example, but to give you an idea, there are different roles in the system, and master and slaves are running on different machine. Right, every slave can be run on one machine, and master is on another machines, and they're running different piece of code, or they're running different because they have different roles. So that's very important to understand. Not necessarily that everyone in this distributed software network is running the same piece of code. Then the next question is, do all the nodes or do all the peers have the same view? What I mean by view is, when you're taking a snapshot of your database, do they have the same data about, of course, particular to this software, because you can have many processes, many software running on your machine, but particular to this software, do every nodes have the same view? The answer is no, and almost always no, right? So if you imagine that you take a snapshot at any point in time, you ask everyone on this network to stop at a certain time, and you take a snapshot of their databases, then it's very likely that different people, different nodes would have different views. Now, why is that? There are three primary reasons. The first is that each node could run different code. They could play different role, like I said, in the Hadoop system where you have master and slaves. So master is probably in charge of different, subset of the data, whereas the slaves are in charge of different subset of the data. So that's one thing. The second reason is that even if all the nodes or all the peers are running the same piece of code, So we're essentially saying there's no master or slaves. Everyone is the same, running the same software. Some nodes could still be out of sync. Why is that? Well, some nodes could just basically go offline, right? Some voluntarily, some involuntarily. You could crash. The computer could crash. So let's say I left my computer there running some piece of distributed software for days, and then I realized I have to close it or update the system, whatever. Then I close the system. When I get back online again after a couple of hours, I would be mostly certainly be out of sync, right? Behind the rest of the network. So that's where I will definitely have a different views than the rest of the network. Now, the third reason is that even if everyone is online and even if everyone is running the same piece of software, people could still have a different views. And the reason is that in contrast with software running on a single machine, updates is instance, and it takes no time essentially, because it's just a read and write operation on the disks, which just take a couple of microseconds, but then nanoseconds. But compared to doing an update in a distributed software, any updates would take some time for it to propagate throughout to the network, right? So then that will introduce a delay essentially. So basically, if you imagine I'm the peer over here, and I want everyone to update the states or update the database, a certain entry of the database, and I'm broadcasting this in the base. Basically, broadcasting means that I'm trying to let everybody know. But this piece of information, as I said, when you are pass through a communication message through the network, it takes some time. So for this guy who's at the edge of the network to hear my updates, it takes some time. That's where when you take a snapshot and freeze at certain times, we most certainly have different views of the current state of the system, and this is a very important point to keep in mind. So just to give you another idea of even if you run the same piece of software, people could still have a different subset of the data. BitTorrent is this very famous and once very popular file sharing protocols that people uses. So, imagine you have a lot of video files. So instead of keeping all of them at YouTube or at Google server, you can just keep it to yourself and just uploading a certain information to the torrent tracker server. Okay, so when people are trying to access certain video files, they're just gonna first of all ask the server indexer, and which will tell you sort of where the file is, and I'm just gonna ask directly to the resource holder for the resource. So in a sense, in the BitTorrent network, in the BitTorrent protocol, there is no it's not one party or the Google server who's holding everybody's files or all the files, right? Each resource is sort of duplicated at a few resource holders, sometimes even just one. So a few resource holders for each file, and the one stores everything. So in a sense, when you're looking at from a satellite perspective, looking down from the gut view to this, looking down on the system, you can see each peer is storing different subset of the data. And this is still a distributed software. So that's just an example for you to understand the first point over here. Okay. So with those two key questions asked, now we can move on to what about Ethereum? So for the Ethereum blockchain, as we said, it's a distributed software, and the answer to those previous questions is that first of all, everyone is running the same software. Okay, everyone is running the same software. It's not like the Hadoop system. Now, everyone is storing the same set of data. I'm referring to the miners or the full nodes over there, not including light nodes. Okay, so for all the full nodes, everyone is storing the same set of data, which is essentially the entire transaction histories and the entire blockchain. Okay, now, but they still possibly could share different views. And for the reasons that we just mentioned, the second and the third reasons, people could go offline, machine could crash, there could be new nodes joining the network who are still syncing up with the history. And for the third reason that we mentioned, which is for any updates to be propagated throughout the network to everyone to heard about that piece of information, that piece of updates, it takes time. So for those reasons, this is a good summarization of what Ethereum blockchain is doing as a distributed software. Now, with one caveat, which is when I say running the same software, is that in theory, everyone who's running a client node or the client implementation should be the same, but in reality they are not. In particular, they have the same specs, right? They have the same specification of how the system should work. And in the Ethereum case, people usually refer to the yellow paper written by Gavin Woods quite a long time ago as the formal specification. Later on, there are many improvement or EIP improvement protocols that improves on the original and revise some of the design decisions written in the specs. But in general, everyone should have the same specs. However, there are different implementation or node client implementation of that piece of software. There are people who write in Golang, in JavaScript, in Python. So different client. Since you can imagine they're written in different programming language, very likely they are not doing exactly the same in terms of the code base and the client implementations. So in theory, they are running the same software, but in reality, there are discrepancies between each nodes. Probably minor discrepancies, but that's still, in some cases, if you are updated with some of the blockchain news, you can see there are, I think, a group of researchers from UCL who's doing this analysis, and he sees that there's actually quite huge discrepancies in terms of the version of your client, and that could cause some inconsistency or even some problems with the consensus algorithm, because you thought people will come to consensus because given the same specification, people are supposed to, if they follow the protocol. But however, the real implementation has discrepancies. So sometimes you could, you could, there's a situation where there's going to be a hard fork because of the discrepancy between the software implementation. Okay, so after understanding the distributed part, the P2P part is quite trivial, right? The reason why we call it peer-to-peer is because it's no longer a client-server paradigm. A client-server paradigm is the one that we usually use or we usually see in today's world, right? Google search, YouTube videos, Dropbox, PayPal. All of these are client-server paradigms where we, the users, are the clients, and the service providers, Google server, Amazon AWS, Azure, these are the server. They have the server. So there's a clear sort of separation in terms of rules, and there's a clear hierarchical distribution of like what do each people do. We're the one who enjoy the services, and they are the one who store our data and provide the services. Now in P2P software or into P2P network, everyone is doing the same job. Okay, you're being a client and a server at the same time. You're serving files for other people at the same time downloading files from other people. Okay, so that's what we mean by P2P. In particular, what exactly do a P2P or a node in the P2P software network do is that on Ethereum blockchain, we listen to all the new transactions that has happened after the last block. We verify that those transactions are valid, the input and outputs are correct, and there's like a correct message and correct signatures, for example. Then for full nodes, you're mining the new blocks. Every full node is mining miners is mining the new blocks, and you're broadcasting a new block if you find one to the rest of the network. And if you didn't find one, then you probably will end up verifying some other people's block. So everyone is sort of doing the same job. Now, the third point about P2P is that everyone will keep track of the same data, right? So as we already said, unlike BitTorrent network, Ethereum blockchain as a distributed software, everyone in the network is supposed to, full node is supposed to keep track of the same data, which is the entire transaction history, the blockchain as we usually refer to it, the entire ledger. Okay, so that was a very high level overview, but once you see Ethereum blockchain from this perspective, nothing is sort of like too scary anymore, right? All those buzzwords is no longer a problem to you when you are looking at from this level. As a developer, to me, it's just a very nice, interesting new distributed P2P software. But from a computer science fundamental perspective, there's it's pretty easy to understand. So now let's just zoom in to the continent level view right now. We just mentioned what would it look like from the system view. Now let's dive in, zoom in into each node. Okay, so what is a node exactly, and what does a node do, right? So the answer to that is just one-liner. Okay, it's a state machine. Every node is doing what they do is that they're acting like a state machine, and that's all. And there are 2 points about state machine that we need to understand. The first is that it keeps tracks of the states. The state of what? The state of the ledger or the state of a database. And it does some state transition, right? So just to give you an idea, especially for those who are not from a computer science background, a state machines basically have different states and legitimate, and you also have to define legitimate transition between different states. If there is one, right? There are states that probably are unreachable. But then in these trivial examples, we can see there are 3 states. All of them are, expressed within the circle. There's work, home, and bed. Those are the 3 states. Now, to move between the states, or what we say, apply a state transition. For example, I'm at work right now, and I'm gonna transit to the state home. Is like I'm gonna take a train. So that's an action that I'm going to apply on the current state, and I'm going to move on to the next state. So that's a state machine, right? So let's say I'm at home right now, I'm going to go to bed, right? So I'm going to apply the action sleep, and that moves me into another state. Now, in the Ethereum blockchain, or any financial scenarios, what that means is that we have a ledger, and this piece of ledger is kind of like a balance sheet. Who has how much, right? So let's say at the very beginning, the state is basically the ledger, the current balances of the current ledger right now. Alex have 5 Ethereum and Bob have 1 ETH. Now, the action is sort of like, or the state transition is, for example, Alice is going to pay Bob 1 Ether, and that will move us to the next state of the ledger. Okay, so that's a state machine. Every node is basically keeping track of the current states and hearing from the action that people want to apply, and who's trying to move the state of the ledger to another state. Okay, so let's say instead of Alice playing Bob, we can have Bob playing Alice 1 Ether, and we move on to another state. So that's a state machine. Now, as we said, there are 2 primary actions that we can do for our node or for a state machine. One is you can read, right? You can look up some states from the current database or from the current ledger, or you can write, by which we mean we can apply certain action. We apply state transition to the current state and update the states. Okay, the states, once again, is the summation or the combination of all the current value of variables that you want to keep track in the system, right? Which basically is a snapshot of your database. Now let's break it down and look at one at a time. So let's talk about read first, right? In Ethereum blockchain, now let's imagine when we're saying like zooming into the continent level view. Now you have to imagine yourself, you're in a node. Okay, you're a node. Imagine yourself you're a node and you're trying to do a read operation. In order to understand read operation, there are 2 questions that we need to ask first. The first is what can be read? What's there for me to read, right? For me to read. Now the first is that first thing that we can read is everything that's related to every account, right? The balances of that account, the nonce or how many transactions that account have already conducted, and the address, which is the account itself, which is the unique identifier of that account, right? Those things can be read, and I'm going to show you in a minute what those things mean. Okay. Then the next thing is every transaction included. Okay, so every transaction that has ever happened is sort of it is readable. Okay, that was the second thing that you can read. The third thing is every transaction received. Now, this can get tricky sometimes because people are sort of confused with transaction and transaction receipt. Now, I think a good analogy of this is that, let's say you go to a restaurant and you buy a soup, and that costs you $15. Now, you paid the restaurant owner $20, and then they give you back $5 in exchange. As a change. Now, the transaction that you do, which is the action that you pay your express, you're saying I'm going to pay you $20. That is the transaction that you signals. Okay, that was transaction that you sent. Then the actual money that you paid is only $15 because essentially you get $5 back. Now, the $15 or the receipt that you get from the restaurant is going to be you spending $15 instead of $20. So that's the differences between transactions and transaction receipt. In the Ethereum blockchain, every time we were sending a transaction, especially a write operation, which we're going to talk about in a little bit, you have to express how much gas you're willing to spend on that operation. And that was part of the transaction fee. Okay, so if, let's say, operating that write operation takes less gas than you are willing to, like in the case of the restaurant where you pay more than actually needed, then the actual receipt is going to be different. Now, in another case, if, let's say, you spent not enough gas or not enough transaction fee, and the gas will run out, then you lost all your gas and you spend money, and yet the state is not updated. So the transaction receipt is going to tell you that state that attempt to update the states is failed. Okay, then so you can see sort of the status of your transaction in the transaction receipt, and these two are included in two different trees, and we'll see that when we get into another deeper level. Okay, but those are the things that you can read. Okay, so right now we're basically talking about what things that can be read. Now, the last category of things that you can read is that some global metadata about the blockchain, including the block headers, what's the previous hash, what's the current block height. Block height, basically, how many blocks do I have before me, right before this block? What's the difficulty level or the hash rate? How much hash can the system do per second? Right? Those are the states that we can read. Now, the next question is that, okay, so good. Then let's say I already know these information I can read, but in what format, right? How do I format my read request in order to get those information out? Now, as a developer, when you try to read those data from blockchain, you should always use some kind of library, and they will build a JSON wrapper around the actual data. And the JSON RPC specs is specified here. For those of you who are not from a CS background, I'm just going to give you an idea of what JSON object is. Okay. So JSON object is just a template or a standard for which we could organize our information into. Okay. So let's say this is all the information about a book. Okay, if you just want to tell other people that, hey, this is the title of the book, this is the author of the book, we can just put it into a banal, a boring string. We could do that, but that's very hard for you to parse out for people who are reading that one. So we can organize it into a JSON object, which essentially is attributes and value pair. Okay, the attributes is title. Then the value of that attribute is that whatever the name of the book is, and there's the author, and the author that the value of that attribute is the Robert blah blah blah. Okay, now if you see over here, for some attributes the value can be another JSON object or a smaller object. So in the details that you have publishers, publication year, the ISBN identifier, the language, how many pages do I have? Now, in order to access, or when you are reading the data, you have to parse out this object and read the actual value, because I don't really care much about how you organize the data. I only care about the actual value. And how do I, for example, how do I know the publisher that are gonna be this object dot detail dot publisher? Okay, that's how you get little brown out. Now, in the Ethereum case, let's say I want to get the current block numbers. Then okay, I believe this is a typo. I think is get block number. Right. I think to get a block number or the current, as we said, some metadata about the blockchain, the current block height. Then we're going to use Web3, which is a JSON object that encapsulates all the information of the current state of the blockchain. Okay, then you can dot using the descendant dot notation to access through the nested object structures. And I'm going to say get block number, and then it will return you the current block numbers. Now let's say I want to know the balances of each account, right? As we said, everything related to every account is readable. Then we're going to say if.get balances. I'm going to pass in a parameters, which is the actual address of a certain account, and it will get me the balances. Okay, so one caveat or one interesting notes to remember is that what's actually being stored on the blockchains are not the JSON object itself, because JSON object is not the most efficient way of storing data. As you can see, there are a lot of like spaces, and to just put that into such an organized way, it took up a lot of unnecessary space or storage. And the most compact way to do that is just to calculate and trim it down into a stream of bytes. And that's how we store things on the blockchain, because everything on the blockchain is sort of replicated throughout the network. Everyone is having the same piece of ledger, so you don't want that such an inefficient data structure to store all the data. So everyone is storing just the string of bytes. And whenever we say like a JSON wrapper, it's just a piece of software that read that string and parse it out and reconstruct that unintelligible string into a readable and very nicely organized JSON object. Okay, so as a developer, I don't really have to care that much about the string of bytes and how you concatenate, how you pack that, how you pack the JSON into the bytes, all the bytes. All I need to do is just use some of the tools that have already done this process for me, who have already parse that information into the JSON object and just read it from the JSON object. Okay. All right. Okay. So that was the information about the read operation. Now let's do some demo. So the first thing is that about Block Explorer. I want to explain what a Block Explorer is. So as already said, there's so many information that we can do, and doing things and reading data manually takes time, and sometimes it's hard to do. So we can use sometimes we usually use Block Explorer to help us do that, right? And let's see. Yeah, so Etherscan is one of the most popular block explorer that we use. Okay. Now, the reason why we call it Explorer is it is exploring the entire blockchain history. Anyone can get the same piece of information out of the blockchain. It's just that they are doing a services and doing this for free to you, so that you don't have to do it manually yourself or running a client yourself. Okay, so you can, all of this information can be verified by anyone who's running the Ethereum client. And Ethereum client is open sourced, and everyone can verify that. So so let's see some of the things that we talk about. Last block, as you can see over here, this is the latest block number, which means that currently we have this number of blocks existed. Okay, and then the hash rate, which is the difficulty level we talk about, which is something that we can read. This is how many hashes that we can do per second for the entire network. Okay, now this is how many transactions that we're doing. Let's say let's first read about the blocks. So the last block that was mined is here, and this is the block number. These are all the information about this block, which are all included in the blockchain ledger itself. The height, when it was the timestamp, which is when was it mined. How many transactions do we have within this block, right? Every block have a lot of transactions. The parent hash, which is the previous hash, the previous block, a pointer to the previous block, right? Who is mining this? Okay, this guy is getting, which is a mining pool, and is getting all the rewards, right? So this is the block rewards. This is how much you get, which is 3 ether. It used to be 5 ether, but after the contest, the last hard fork, we scale down to 3 ether. And what's the size of it? What's the difficulty level? So on and so forth. Okay, so let's click on all the 90 transactions that we included into this block. Once again, these information are you can read directly from the blockchain, but this block explorer just help us presenting a nice UI for us to interact with, so that we can get those information more easily. So let's say this transaction, we just click on any random transaction. This is a transaction, okay, and this one is the transaction hash, which is a unique identifier of this transaction. And the reason why it's a unique identifier is that this hash is computed with the information that's particular or that's unique to this transaction itself. And every transaction also have information related to it. There's a token transfer, which is a ERC20 token transfer happening within this transaction. It happens from one, I guess this is an externally owned account, to a contract account. Okay, so from someone to someone, and all of them are represented by their public key, the hash of their public key or their account, their address. And there's the gas that this guy have used for this transaction to take place. And you can also pass in some of the data. So this input data, I'm gonna explain what does this function transfer blah 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 means, right? Essentially, just very briefly, this input data within this data field, you can express which function you want to call to a certain contract. Smart contract is just a piece of code. So within the data, you can specify, hey, I want to call this function under this piece of code, and here are my parameters. Okay. Okay, so that's all information about transaction. As we already mentioned, we can read balances of account, transaction receipt, blockchain data. Now we can also see, let's see an account. All right, let's click on any random account. So this is an account. This guy have this amount of ether, okay, and which is basically this amount of only 2 cents, right? This guy is apparently very poor. No, I think this is a smart contract. This is a smart contract. Yeah, that's why. This is a smart contract. Let's click on another one. Yeah, this is another smart contract. Huh, interesting. Wait, is it? Okay, I'm not sure. Does it say it's a smart contract? Yeah, so this guy apparently have like 1.8 ether. This is the balance of a certain account. How much is that in USD? This information is not stored on Ethereum. Okay, this is using some kind of data oracle and translate that into, if we're assuming this exchange rate, this is how much USD dollar value that it has. This is how many transactions this account have already done, which is called the nonce. Okay, I think that's enough for the demo over here. Now let's go back. Another thing that we can use is using Geth. Okay, Geth is just a client that you can use. Now we're gonna do like a live demo of the current blockchain, reading data from the blockchain using just some command line tools. So the one I'm gonna use is Galanchi, and we're gonna connect into one of the testnet and see what's going on. So just to save time, I already truffle init my this folder, as you can see over here. So under this folder, I truffle init, and I, basically, let me. All right. Okay, so as you can see, there's a truffle config. Give me a sec. Right, so there's a truffle config file, and for me, in order for me to use the inferior network and to connect to the live testnet, I'm gonna have to pass in my inferior key over here. Okay, over here. So this is the inferior key that I have to pass in, and okay, let me just zoom in a bit so that you can see. Yeah, this is too big, right? So I'm not gonna show you my key. You can apply it on the inferior.net.io. So this allows me to use the inferior network services and to read data from the live network, which is Robston. Okay, I'm using Robston for now. Okay, now. Okay. First of all, we have to fire up the truffle console, and we're gonna use the network, and we're gonna specify it as Robston. Okay, so whenever I type this comment, what I'm doing is that I'm telling Truffle to please connect using the console and connect to the Robston testnet. Okay, so good. Now if we type web3, let's just clear things out. Wait, sorry, that's not comment. I hope you can see my screen. Okay, if I type web3, what it will give me is a huge JSON object. Okay, so within this JSON object, there's a lot of things that we can call. Now, the first thing I want to do is I want to know what's the current block height, right? How many blocks have already been produced? So as we already said, there are a lot of things we can do. We can get block number, if I'm not wrong. Great. So I hope you can see over here. This is 49 blah blah blah. This is how much that we how many block has already been produced, according to Truffle. Now, in order to verify that, let's go to ether counter. So Robston. Okay. Over here, this is the Robston the Etherscan block explorer, but it's for Robston testnet. Okay, so this is the URL. And as we already see over here, we're like 2601, but actually currently we're like far behind. We're far behind. The reason why is inferior network inferior network is, sorry, give me a sec. Inferior. Okay, the network is slow. So this is Infura. They're hosting full nodes for us, for developers especially. They are caching the blockchain data. So they're retrieving every other seconds, I would believe. But they're not giving the latest status, because sometimes there's going to be reorganization of the chain. Sometimes there are different competing chains, and you haven't decided which one should we settle first. So they will give you like the more stable ones. So that's why when we're getting the block number or the block height, it's sort of behind the current status, the current state, the current block height, like the current block number. Okay, so that's the first thing that we can read. Now, another thing that we can read, for example, is that let's say, let's open up our file. Okay, so let's go to Robston. So on Robston, I have a few test ether. This is the balance of this account. Okay, so let's see how do we read balances of certain account. So as we already said, we can use balances, get balances, and we're gonna pass in an account. and this is my account. Okay, so when we're doing this, you're gonna get information like this, which is basically saying, as some of you probably feel strange because I don't have that many ether, but this is expressed in the unit of gas, in the unit of weight, which is the smallest denotation in Ethereum blockchain. Now, as you can see, I have 2.4714 ether, and over here I have this many. So if you divide this by 10 to the power of 18, you will get exact number in terms of if we're using ether as the unit. Okay, sorry, I think the network is pretty slow. One way for us to do that, I think, is if we can use utilities. I'm not sure they have this. Yes, I think to Frontway, if I'm not wrong. Okay, we can use this. Oh shit. So Web3 using their utilities library, Frontway, and I'm gonna pass in I think it's strange because it requires a string. Yeah, there we go. So basically, it translates this number from way, which is the unit, right? From way to ether, okay, which is 2.4, which is exactly the same as how much I would have over here. And if we go to view it on Etherscan, which is the block explorer that we just mentioned, notice here, this is Robson Etherscan. It will tell me exactly the same how much I had over here. Okay, so that's how you read data from blockchain using truffle, right? And later on I'll show you how to read that using Galanchi. But that's mostly for testing purposes. Okay, I think that's enough for this demo. Okay, let's move on to the next operation. Okay, the next operation is write. Okay, we'll talk about read, and the next thing is write. Let's say we're currently at block number 230, right? We have 229 block before me, and there are a lot of transactions happening after this block is being found. And after applying all this transaction, we move on to the next block, which is another state of the ledgers. Okay, so in a sense, as you can see, the ledger is the state, and all the transactions are the is the action that we want to apply, or the transactions, the state transition we want to do. Okay, so there are also a few key questions. The first is, how do we modify the blockchain? How do we modify? What's the action that we want to apply? Right, as we said, from work to home, I have to take a train. That's the action, right? That's how we apply the state. That's how we modify the state. But then, how do we modify the state in blockchain? The answer is, we're gonna do it via transactions. Okay, so the command for state transition is basically is done via transactions. And you can contain all the necessary parameters within these transactions. So what I mean by parameters, okay? So let's take a look. Sorry. Yeah. Oh yeah. Sorry. Let's take a look at the transactions. So within these transactions, there are a lot of parameters that are being expressed, right? For example, from which account to another account, how much gas you're willing to pay, how much value or how many money you want to send to the recipient, right? Those are all information, okay? Those are all parameters to that transactions. Now, transaction is no longer just for balance update, but arbitrary state updates. This is very important, okay? So compared to just a normal ledger that keep track of a balance sheet, that keep tracks of how much money do every account has, Ethereum, as we said, is a general purpose computer. And what that means is that you can run arbitrary program on it. Every program, as you can imagine, have different variables. And the value of those variables are usually called, like, what we refer to them as the arbitrary state. Now, you can change the value of those variables through transactions, and that's what we mean by arbitrary state updates. Okay, so the next question is, then, okay, we know how do we modify to blockchain just through transactions and include necessary information in the transaction. Now, what constitute a legitimate write operation? Okay, first of all, we have to clearly specify which state do I want to modify. Okay, whenever I say like Alice, for example, if Alice want to send some money to Bob, then it is the Alice and Bob's balances that we want to modify, not the rest of the states, right? Not the other states. Now, so that's the first thing. The second is, how much do we want to change? What's the differences? What's the new value of that states, right? Of that variables? And also, how much gas are you willing to pay? How much transaction fee are you willing to pay? And the next thing is, you have to provide a valid signatures. You can't just change other people's balances, at your free will. You have to provide the correct signatures signed by your private key that's only known to yourself, to authorize a legitimate right. So those are a legitimate right operation. Excuse me. So that's basically how you do it. In order to do a demo, or to give you a more detailed view, because the right operation is the most important part for any developers who want to use blockchains. So we have to zoom in another time into the city level view to understand the right operation. And I'm going to give you a demo later on. As we said, for a legitimate right operation, you have to specify which states you want to modify first. Okay, so in order for you to correctly and accurately point into the states that you want to modify, you have to know how states and how variables are being stored in Ethereum blockchain first. It's the same thing like, you say you want to change the poster on certain building in Manhattan City, in New York City, on the Manhattan Island, yet you don't know the internals or the grid system of the Manhattan Island. Then there's no way for you to instruct other people to do that for you, right? It's hard. So in order for you to find the Fifth Avenue, you have to understand the grid system, right? It's the same thing for any developers who want to write something, who want to change the state of a certain variables in the Ethereum blockchain. You have to understand, how those states are being stored. So this is something we're going to use to help us understand, right? Now, for those of you who are watching at home, or who are, who want to have a better, higher quality, picture of that, you can go to bit.ly/lazyasme. It's the same link over here. Okay, so I'm just gonna click on. All right, so first of all, this is not my work. It's sketched out by someone extremely awesome. So this guy read the yellow paper, okay, and then it sketched out how it works over here. And I think by far this is one of the best explanation, at least for beginners, for us, for developers. This is amazing references for us, to take a look, and without looking, we don't have to go through the entire yellow paper to look at all the mathematical notation and to understand. So okay, so the first thing that we noticed in this illustration is that there's this chain, right? There is this hash pointers that we refer to, and this is the data structure that we use to store the block headers. Okay, the block headers. So each new block is appended to this chain of blocks. Okay, and when we're referring to the block, there are a lot of information that's included in that block, right? And specifically, we talk a lot in what's included in the block headers, which are mostly the metadata about the blockchain. Now, if we zoom in a little bit, we can see the block headers have a lot of fields. Okay, the first fields, let's say, is the parent hash. So the parent hash, as you can see over here, is a pointer to the previous or the last block that I'm appending to. Okay, now this has to be correct. This signifies which parent does this block have. Okay, so and this hash value is basically the hash value of this entire block headers. Okay, Now, other than that, we have some other information: the state root, transaction receipt root, and a lot of other information. So this root hash, if we can still recall the Merkle tree structure that we talk about, is the value of the root hash of 3 separate Merkle tree. Okay, each one of these Merkle trees are in charge of keeping track of different things. For the state tree, they're keeping track of the accounts. Okay, the value or information about the account. For the transaction tree or the transaction hash root, right? It's from the transaction tree. Transaction tree is keeping track of all the transaction. Transaction receipt tree is keeping track of the transaction receipt, apparently. Now, I'll talk about those in a little bit, but other than that, we can see there's difficulty level, there's the block number, there's the gas limit, how much gas have you used within this block, and some extra data and some nonce. We can just explore. We can just ignore those for the moment. Some information about uncles, how many uncle rate do we have? Then those are not so relevant for this talk, but we can cover in our future episodes. Now let's take a careful look. So those are the block headers. Okay, those are the information that even the light node is gonna store. Now let's take a more detailed look at the 3 different Merkle tree that we talk about. The first is the state tree. Okay, the state tree, as you can see, is a mapping between the addresses and all the account states, right? And everything is stored in the Merkle Patricia tree. So at the bottom of this tree is each account, every account. So as you can see, my account over here. So this is the unique identifier, right? Which is the address. Now this address, this is too big. Sorry, give me a sec. Okay, so that address that you saw just now would is a unique path from the node, from the root hash all the way down to the leaves. So that would point you, for example, to this node. Okay, I am the account over here. Now, what's inside each one of these accounts is another set of information. Within each account, you will have a nonce, which means how many transactions have already done. Okay, have already done. Now, just to give you an example, this is my account, and this is my nonce. My nonce is 100. My nonce is 105, which means I have done this number of transactions in previously. So that's the nonce. Okay, another one is the balance. How much balance do I have under this account? And I have this number of ether. Okay. Now there are other information, which is the storage hash root. Once again, Merkle tree. So it's like a Merkle tree inside a Merkle tree inside a Merkle tree, very nested Merkle tree. Now this Merkle tree, this storage root, is particularly for contract. Okay, so imagine if you're a smart contract, if a piece of code, then you have a lot of variables. As I said, those variables are also organized in the Merkle Patricia tree. And for example, this is the variable of, I don't know, certain integers in that program, and this and at the bottom of this one, you will see the value of that integer currently. Okay, so that's the storage root. So whenever we're talking about like a smart contract account, and we're talking about certain global variable inside that smart contract, you are talking about you are basically, you have to traverse first of all from the state tree, and then look at the storage root. Goes all the way back into this particular the value of that variables over here. Okay. Another thing is that if you're a smart contract, then you will have a code, right? You have, if you're a program, then you have code, and then the code hash, right? This is used to make sure the integrity of the code that you're retrieving is correct. Okay. So that was about the account. Now let's take a look at another tree, which is the transaction tree. Transaction tree is a tree that keeps track of all the transaction. Within each transaction, there's also the nonce, the gas price, how much price do you willing per gas, the gas limit, because the transaction already specified the signatures. So from someone to someone. Okay, so this is the recipient. How much money you want to transfer along this transaction, which is the value, and also the data. Okay, this is very important. as we said, within the data, you can specify if the two or the recipient is a smart contract, and you can specify what function you want to call in the data field. Okay, so for developer perspective, as we said, if you want to interact with this general purposes computer, you have to know how to call a certain function. That's exactly why whenever, let's say there are many ERC20 token smart contract in the world, right? Whenever you want to say do a transfer, you do not want to call a function on different ERC20 tokens. Okay, so what I mean by that is that imagine there are two pieces of programs that have exactly the same piece of code. Okay, how do you make sure that whenever you call a certain function, the Ethereum network do not mistaken that because the two programs have the same piece of code. Okay, so you have to specify, which state you want to modify exactly. And that is how you do it, right? Because different smart contract would have different account, different address, right? There are different entities over here, and that's why you will have a different recipient when you try to call a certain function, particular to that function, particular to that smart contract. Okay, so that's how you avoid, for example, like to avoid any ambiguity in terms of like calling a certain function. All right, so that's very important. Now, transaction receipt, is less relevant over here. But as you can see, I would strongly encourage everyone in our club and those who are watching this to take a good look at this very great illustration. I'm not even going through how the RLP, this encoding works, because that was a little bit out of the scope for this talk, and how you represent all the variables into such a Merkle tree. How do you do that? But we can do it in the future. Okay, all right. So that was the city view. The grid system for Ethereum blockchain? How do we store each state, and where do you find each state? Now let's do some let's do some live demo. Okay, the first is as we talk about, there are two types of accounts, right? The first is externally owned account. The other is a contract account. Now let's try to create a new externally owned account using Truffle. Okay. Now this is the Truffle console that we just had. Let's imagine that we're connecting to Robston. We don't necessarily need that, but yeah, we can do that. Web3 dot ETH dot I think accounts. I think you have create account or something. Yeah, create. Great. So whenever we call this function, web3.eth.accounts.create, then it will create a new key pair, and this is a externally owned key pair. Now this is the private key for this account, and this is the address, so you can tell everyone about this account. Okay, this is the public information that you should tell other people whenever you want them to send you some Ether or interact with you. Now this is the private key that you should keep it to yourself. It's okay for you to see my private key over here because I would never gonna reuse this account ever. So it's fine, but you can use this account. This is how you create an externally owned account. Now this is not the only way you can create accounts, okay? Because this algorithm of creating this key pair is public, okay? Using this Web3 or this Truffle, developer tools or this Truffle console is just an easier way to do this. But the actual implementation of the algorithm, it should be public and the same as the specs. Okay. Now this account, let's show you how do you read balance, how do you read nonce. Okay, so let's web3.eth.get balance. Once again, we show you how do you get. Let's have this. Great, 0. So currently there's no money inside this account because I just created this account, right? No one has already sent any money to this random string previously, so that's why I have 0 Ether in my account. And how much nonce do I have? Yeah, so I think web3.eth.accounts. Do I have the set value, create encrypt, sign, wallet? Wait. Wait, where? Get code personal, is it? Wait. Get transaction account or something like that. I kind of forget where is that because it's sort of changing. New account. Providers and transaction. I kind of forget where. How do you read nonce? Oh yeah, get transaction account. There we go. Sorry about that. Get transaction account. I'm gonna use that again. It's 0. Okay, it's 0 again because this account, I just created that account and I have not done any transaction yet. So let's say if I pull the account that I have and I have done quite some transaction previously over here, then we should see probably a different number. Yeah, we should see a different number. Yeah, there we go. So we have like a 93 transaction previously, and these 93 transaction I would assume does not include any call to contract or something. Why is it different? Okay, I'm not exactly sure. So there are subtle differences, as you can see. If let me see, I think there's just one point I want to make. Okay, so when you are visiting the Etherscan website and the URL address does not have a capital letters, but the actual address have. Okay, I just want to point out this point, right? For example, this E is capitalized, whereas this E is not. All right. Now the actual account does have capitalized letter for integrity checks. Okay. Yeah. So that's just one point. So when you are decoding, we were signing information. The thing that can output when you're providing signatures and you want to check whether it is actually from a certain account, the capital letter actually matters. So as an integrity check. So that's just one point I want to point out. Now the next exercise we want to do is how do we create a smart contract? Okay. Now in order for us to do that, we first of all have to have a smart contract first. So now I have written a smart contract previously, just for demo purposes. So as you can see, oh wait, sorry, this is the counterfactual thing. Yeah, so there are two smart contract over here. The first is the one that came along with the travel init migration. The other is the minimum, which is the one that I wrote. So let's take a look at the minimum. All right, so this is smart contract. So this is smart contract, very minimum. There's a constructor which do not do anything at all. There's a greeter over here, and it basically return hello, a greeting message. That's all. Okay, this is the smart contract that we have right now. Now one way to get a smart contract address, or to deploy a smart contract is through remix. Sorry, this is. Okay. Minimum. Let's see. I'm gonna sorry, I didn't copy paste. Damn it. All right, so we got this, and we can compile it, and let's not use this, just use JavaScript. Okay. Wait, 11.5? What the heck? Wait, sorry. Yeah, sorry. I did some rare changes previously. My bad. Should be fine, right? 0.5. Choose the correct compiler. Should be fine right now. And we can deploy. Now, once we click, okay, I think this is probably too small. Just now what I did is I click deploy, and we're running on a virtual machine, which is basically a sandbox that's only running locally on my machine. What happens is that when you're deploying a contract, then you're basically sending a transaction. Within this transaction, you have a huge piece of code under data field. So in the data field, you are passing along the entire bytecode or the compile, the actual code itself, not on the high level, but like bytecode, 0, 1, or hexadecimal string. So this is the data. This data is, so this data is basically the code itself to the network. And this is one of the parameters that you send through the transactions. And through this transaction, people will update the code session, the code variables under that account. Okay, that's basically how you deploy a smart contract. And you can get this is the address. Okay, this is the address, and you can call a certain function of that address, and it will returns you hello. Right, it returns you hello over here as expected. Now, in order for you to do that. On your local machines, right? So what we can do is, usually what we do is we fire up a Galanchi, which is also a command line tool that fires up a local testnet. Okay, so it's not a testnet, but like a private blockchain. It's only accessible to you. It's running locally, like a sandbox. It's usually used for testing purposes. Now, there are a few things over here whenever we run. So you can see this is a Galanchi. It's running, and I can make a use of 10 accounts. So each account have a roughly 100 ether over here, and it's listening on a certain port. Now, instead of connecting to the testnet, I'm just gonna connect into this developernet. So as you can see, we already have the contract written. So if I want to deploy a certain contract, all I need to do is truffle migrate. So when you type truffle migrate, okay, let's take a look at all the information, all the message over here. So when I truffle migrate, it's compiling my contracts and it's deploying the contracts, right? The network name development, which is the network that I'm happening over here, and it's running my script, my migration script, and it deployed 2 smart contract. This is a smart contract that I get over here. Okay, so this is a transaction hash. This is a contract address. This is how much account I have. So let's see over here. Let's copy this and let's fire up truffle console network development. Okay. Now let's try to read what's happening of that address. If you see over here, actually you can see that. So this is the transaction that we just saw. We just read, right? Now if we saw my cursor over here, web3.eth get transaction. Now I passed in the transaction hash, which I just copied right there. You can see all the information about that transaction. Okay, this is the transaction hash. This is the nonce, the block hash, the block number. There are only 3 block number. You may wonder why, because it's a local, it's something that's running locally. So there's, it's nothing happened before this deployment contract. From certain account, this is, I believe, is my account, the account that's given by the Galanchi by default, right? By the Galanchi client server. So as you can see, the input over here, this is something that's interesting. The input is going to be in the data field. Sorry, this is the input field. Oh, sorry, it should be in init or something. Okay, the input is the actual bytecode of this program. This is the program. Okay, it does not look as nice as the Solidity smart contract because the Solidity smart contract is essentially, eventually compiled down to this bytecode, and yeah, and the VRS is just 3 components in my signatures. So this is what happens when you're trying to deploy a smart contract in Ethereum blockchain. You have to provide the signatures, and the signatures, you didn't see the process, but I have the private key, so Truffle has done it for me. So automatically that feels smooth, but what happens under the hood is that I sign this transaction, and putting our VRS together, you can get my signatures back, and people will have to verify the signatures and see whether all the information matches. Okay, so that's how you create a new contract account. Right. So now the next thing is, how do we do a write operation on the blockchain? Now there are 3 exercises. Okay, let's first do a simple payment. How do you do a simple payments? Okay, so on the one hand, if you just want to do a simple payments, you can use in the real testnet, you can use MetaMask, send someone some ether, right? You could send, let's say, you can send someone. This is from my account to some recipient account, some ether, okay, and then you just click next. All right, I think this is pretty trivial, but the one that I want to demonstrate is how do you use the one on my using Galanchi and using Truffle console. So as we can see, we have web3.eth.get account. We have a list of accounts, right? We have a list of accounts. And what we want to do right now is we want to, just give them the name so that you can remember it quickly. So let's say we have Alice, and this is Alice. Okay, just make sure Alice is here. Okay, great. And this is Bob. Okay, Bob is this address. Okay, just make sure Bob is here. All right, so we assign these 2 accounts, to Alice and Bob, and I have both the private key of Alice and Bob. Okay, so this is only for testing purposes. Now, whenever I want to do a transaction, do a transfer or payments between the 2 accounts, I'm essentially have to apply a state transition, as we already mentioned previously. This state transition is through transaction, so we have to do a transaction. So over here, we're going to do send transaction. Now we have to specify some variables from Alice. Before this, we have, let's see how much money do Alice and Bob have. Okay, let's see how much money do Alice and Bob have. So let's see web3.eth.get balance Alice. Okay, so this is how much Alice have. Now let's see web3.eth. Okay, no, sorry, let's just use I'm just being stupid. It's a long session. Okay, this is how much Bob have. All right, so let's see. Let's do a transaction and see how much value does that change. All right, so web3.eth. Send transaction. We're gonna send from Bob to Alice. How much money do you want to send? We're gonna specify in the value. Now, in the value, usually, it's still specified in a way, right? In way, but it doesn't really matter, right? We don't want to just keep track of how many zero. That's just boring. Let's just type in some random number. Okay, let's just type in some random number. Okay, all right, sending that. Now, what you can see is you get a transaction receipt. This is the transaction receipt that we get. All right, from certain this is the Bob's address. This is Alice's address. And this is my signatures from Bob. This is a signature from Bob. Okay, so now let's check again. How much Alice have? How much Bob have? Now you remember Bob used to have like one with a trailing zero at the at the end. Now it has less than that because it has sent some money to Alice, and Alice has more. Okay, so that's basically how you send a simple payments or send money from one account to another. I hope that's clear. Contract creation, we have just demonstrated that both through Truffle and through Remix. Okay, so the last exercise is how do you do like a function call. We demonstrate how to do a function call on Remix just now, and how to do a function call in using Truffle. Usually you will use some test script. Okay, so let's take a look at the test script that I wrote. So in the test script, first of all, you have to instantiate your the contract API. Okay, a contract API is just the interfaces. Give me a second, I have to charge up my laptop. So the API is the interfaces to the actual contract code, because different contracts have different functions, and we have to know all those information so that whenever you are saying I want to call someone, people know which contract you're actually calling. Sorry, give me 1 second. All right, so in this testing script, as we will cover in greater details later on, but in this testing script, you could see that I have one testing scenario testing script, which is I'm gonna first of all deploy over here, deploy this contract, okay, because it's asynchronous. I'm calling the blockchain, so I'm using async and wait. Then what I do is I'm gonna call. I will get a result. Okay, I got the instance, and I'm gonna call a certain function of this instance. This instance is just an instance of that piece of code that you just saw. Okay, the piece of code that we just saw over here. Okay, so this piece of contract, I already deployed this contract over here using this one, using this over here, and then I'm gonna call one of the function which is called greet over here, and supposedly I should get a result out of this. Okay, so I will return the result to a variable called result, and this result supposedly it should be hello, because I said it should return hello. Now I have assert. Assert is basically saying if, let's say, the result equals to hello, then it will not assert. Everything goes well. Now if it does not equals to hello, then it's the wrong message. Then probably something goes wrong. Okay, so let's see what goes on when we say when we try to truffle test. So truffle test would run all the testing script that's specified under the test the test subfolders. Okay, so as we can see, when we were testing the script, we passed the testing script, which means that we get the right outcome, and that's basically how you interact with your contract as a developers. Okay, but we were going to cover, it's okay if you did not understand everything, because there's a lot of tools involved: Galanchi, Truffle, testing framework, testing script, everything. As you already, if you can remember, we're going to cover all of these in greater details in our next lectures. Okay, great. So that's the demo. I hope that gives you a better sense of how to write to the blockchain, how do you write through transaction in particular on the Ethereum blockchain. Now, I hope you have a holistic understanding now. Just to quickly review, we started out with a satellite level view, which is the distributed P2P network. Distributed P2P software. And then we dive into each node, right? Each node is just basically a state machine that keep track of the state and apply state machine. And apply state transition. State transition are specified through transactions, and each transaction specifies from which account to another account, what are the data, what are some of the value that you pass along. Now the last one is how, since we want to specify all the parameters of a certain transaction correctly, we have to know how the states are being stored, how they are organized. So for that, we have a very concrete view of how all the states are being organized, and we give a deep dive into that. I think that basically concludes this lectures. Now my name is Alex, and I'm also working at the Blockchain NTU. So you can contact me at my Twitter handle at @luoyuan, or you can just contact me through our NTU Blockchain NTU Telegram group. Contact us, and all of these recordings and slides we're going to be available later on. Thank you very much for your time, and enjoy hacking.